All right, class, this is our first day on Kirchhoff's laws. This is in our Unit 5 objectives, Objective 2. We see it down at the end for using Kirchhoff's circuit laws to solve for potential difference, current, resistance, and power. We're going to need to really take what we've learned previously using Ohm's law, V equals IR, R equals V over I, and our power P equals IV, and apply that to our Kirchhoff circuit laws, which we see up at the top right here. So that's what we're covering today. So we will be done with 5.1 and 5.2, technically, all the equations by today. And then just kind of find different ways that we can apply these strategies to understand circuits. So in a warm-up, I want to first calculate the current in the branch with the 10 ohm resistor in number 1, and calculate the voltage across the 11 ohm resistor, given that we have 60 volts in the first one, and we have 4 amps in the second one. I'm going to pause the video. You can solve and then check our work. All right, we see that in our first circuit we have resistors in parallel, and we know that resistors in parallel have a constant voltage across each resistance. We recognize that in number 2, the circuit number 2, it's a circuit that is in series, which means it will have a constant current across each of the resistors because they're all in line with each other. The current can't be faster in one part and slower in another or greater. They're all equal. And we're going to need to remember that the voltage dissipated across a resistor is equal to the current traveling through the resistor times its resistance. And we can use this to solve for the current in this situation where we have a 60 volts traveling through a 10 ohm resistor. So we can find the current traveling through the resistor 2 to be 6 amps. In the second one, V equals IR as well, but current is constant, so we'll just do V equals IR to get 44 volts. This V equals IR is going to be helpful and simplify further problems, but sometimes it's not going to be, we're going to need other strategies. And so we're going to start off with this first law, which we've already used, but we're going to really give it a name and start applying it in different ways. So there's 2 ways to say this. I prefer the first way. The second way is also true. And that is the sum of all currents going into a junction, where this is a junction, this is a junction, all of them going into a junction equals all of the current going out of the junction. Similarly, if I just subtract I out, I can say that the sum of all currents going in and out is equal to 0, knowing that, you know, like one of them is going to be positive, one is going to be negative. So, for example, in this situation, we have an I1 coming in. That's going in. Let's use actual. I1's coming in. I'm subtracting I2 because it's going out. I'm adding I3. I'm subtracting I4, and then I'm adding I5, and that should all equal to 0. This is the same as just saying all the currents going into a junction, such as I1, equals all the currents going out, such as 7 and 4. So this is like saying 11 amps is equal to 7 amps plus 4 amps. And we just did this in class, recognizing that the currents add up to like this total current. And this is because as electrons are traveling to the junction, they're going one way or the other. And either that means electrons cannot be created or destroyed, so their mass can be created or destroyed. So since we're dealing with charges, though, this is technically that represents the conservation of charge. Saying since electrons are made up of charges and current are made up of electrons, that means that this conservation of current is actually a conservation of charge. All right, we've applied this before. But this second law is the one that's a little tricky to use. And we're stating that in a loop, in a circuit loop, such as the one I'm drawing right now, that the sum of the voltages is equal to 0. And so we need to identify like how do we draw a loop? And so we can draw loops clockwise, or we can draw them counterclockwise. It's going to change the way that we identify what's being added or subtracted, but either way, they are just kind of they're opposites of each other. I'm going to show you the way that I like to draw the loops, and then you're going to kind of adapt that and use it. So that's one loop. In this series circuit, there's only one loop where the voltage from the battery plus the voltage dissipated in the resistors are equal to 0. And so we're not just summing them together. That means that E is positive in this case, and then like V1, V2, and V3 are negative in this case, which means there are differences between positive and negatives. And think back to when you played with the voltmeter in the FET, and you moved the red and the black pins of the voltmeter, and you would get positive voltages or negative voltages. So we're going to have to think about that a little bit more. Let's look at our parallel circuit to kind of make sense of that. So we recognize that a voltage is constant across each of these resistors, and that is because at the beginning of each of the junctions, we should have 15 volts, and we can start thinking about seeing voltage dissipated across resistors, and in this case, right, we would go from 15 to 0 volts. So that means as we're moving through one of these branches, we're going from a high potential, here's high potential, to a low potential. Oops. But when we draw loops, our loops might not always be going from high potential to low potential. Let's try to draw some loops here, because in this series circuit we only had one. I believe there's 6 in here. So I'm going to draw a few, and I want you to imagine where the others could be. So the obvious one is around the first battery and resistor. And then I can go to the next little branched loop, and that's also one going to happen like this. Similarly, I can go on the outsides, and I can go like here and completely go around the circuit. And similarly, I'm going to draw this in green. I could even find any loop that I want. It could be like this. And when we think of these loops, we're actually imagining like which parts of the circuits are we touching. Like there's one loop. That's that first loop that I drew. I'm going to get rid of it. Let's look at the second loop I drew. Okay, I passed through here, passed through that resistor, and I passed through this resistor. That's the second loop that I drew. The big loop is going all the way outside. And as we're thinking about this, we're thinking about what batteries are we crossing in this loop and what resistors are we crossing in this loop. And then the green loop that I drew is like starting from this resistor and then working its way down and passing that junction and going to the next one. And so in each of these situations, we're passing through either batteries or resistors that are either going in the direction from a high potential to a low potential, or from a low potential to a high potential. So like for example, in this green loop where I'm starting pretty much right here, and I'm crossing over this battery, and that's going from a 0 volt to a 15 volt. So I'm going from low to high, I'm gaining voltage in quotes. And then as I continue going around, I see that I'm passing across this resistor, and I'm going from a high potential to a low potential, so I'm losing that 15 volts. And then when I finish the loop, I should have 0 volts. I've gained 15 and lost 15. All right, so this might be a little confusing, but we're going to do some practice with this. But all of this is saying is that we will always, whatever voltage we gain in a loop in a circuit will be lost as well. So like the sum is 0. And we know that voltage is the units of voltage is joules per coulomb. So when we say what type of conservation law is this? This is a conservation of voltage, but voltage is just another way of saying energy. So this is right, electric potential. So electric potential energy. And so we've already kind of identified that there are times when passing across a loop that we will be passing from a low potential to a high potential. So this is like loop travel direction. And there are these rules, or you can just think through the high potential, low potential. But I think these rules are useful just to remember. So we're going to be referencing these rules as we're drawing our loop equations. If our loop direction is in the same direction as our current, then we should be going from a higher potential to a lower potential. If our loop direction is going against the direction of this current, then we should be going from a lower potential to a higher potential, and we're gaining current. One way I like to see of this I is the direction that we say positive charges are going, but I like thinking of I as the direction of the electric field through a circuit. And we know that the direction of the electric field is the direction that a positive charge would feel, and therefore it would be going from a higher potential to a lower potential. So the direction of the current is the direction from higher to lower. So if we're passing in the same direction as that field, then we're losing voltage because we're going down in voltage. We're going the same direction as the field. But if we're going against the field, then we're gaining that voltage. Like think about gravitational fields, right? When you go against the field, we're gaining potential energy. So we're gaining that potential, positive IR. It's also important to know that it's positive IR. It's also just positive delta V if we already know the voltage dissipated in the resistor. The battery ones I think is a little easier because we're either moving to the positive terminal, which is like adding that voltage. The battery is kind of restoring that voltage in the loop, or we're going from the positive terminal to the negative terminal, in which we're losing that voltage. And in this case, they use the term E. This is what's called electromotive force, and we're going to be talking about that a little more, but it really just means voltage. That just means voltage. Okay, so I've got 3 examples. We're going to do a series circuit, a parallel circuit, and we're going to do all the loops for it. And then we're going to do one that is a little bit harder. It's a parallel circuit, but I've added a battery in there. So we have this startup guide. Our first goal we're going to do is label all the unique currents. So I would go here and I say, hey, I'm in a series circuit. I only have one current, and I'm just going to call it I. Okay, that's done. My second step, I'm going to label all unique loops. Let's do it. Yeah. In this case, my loop, I'm just going to draw here. And you can see I started off my loop. I like to start off my loop on the positive terminal of the battery. You'll see why that'll be useful when I write down my loop equations. Write down my loop rules. So I need to write down my loop equations. Let's call this loop 1. There's only one loop, but that's what it's called. And I'm going to use my rules to understand how I'm gaining or losing voltage. So I can think of my loop as, okay, I'm passing across my resistor here, passing across resistor here, and passing across resistor here. And I'm also passing across my battery from my negative to my positive terminal. I like starting from my positive terminal because it's telling me that's where my battery's voltage, or that's where my circuit's voltage is coming from. And then I'm passing through an R3, an R2, and an R1, given some current I. So what rules do I have? Well, this is my first rule I'm using because I'm going from I'm starting at my positive terminal, or I'm passing from a negative to a positive. And then my loop direction is in the same direction as my current, so I'm going to have a negative IR being written. So my first loop equation is 40 volts minus, and then I'm passing through R3 with a current of IR3, minus IR2, minus IR1 equals 0. Our loop equation is done. There are no junctions, so there are no junction equations. We have a table, but since this is a simple series circuit, I want you to first, in these problems, solve using what we know about series circuits. So that's knowing that our R total is equal to 10 plus 40 plus 5, so that's 55 ohms. And then we also know that R is equal, or R times I is equal to V, and also, I'll move this over to the side, and also that I times V is equal to my power. So use that information and solve for the rest of the values. I'm going to pause this, and when we come back, I want you and myself to be done. All right, let's get ready to check our numbers. That's what I got. 0.73 is the current. Since we're in series, the current is constant, it's I. And then I got these voltages and this power. The voltages are close enough to add up to 40 with rounding errors, and the power is conserved again with rounding errors. And then it says verify these values using your loop and junction equations from A and B. We really only have part A, so I just need to make sure that this 40 minus IR3 minus IR2 minus IR1 equals 0. So I get 40 minus 0.73 times times 10 minus 0.73 times 40 minus 0.73 times 5. You might notice as I'm writing this that this is just our voltages distributed across V3, V2, and V1. And 7.3 plus 29.2 plus 3.7 should equal 40. And so we're really just redoing that. If I were to check this, this is 40. How did I write that? 40 minus 7.3 minus 29.2 minus 3.7, and that's equal to 0. That's close enough. That's with rounding errors, it's close enough. Let's verify these values using energy power conservation laws. I've already calculated power, so we just need to make sure that 29.1 is equal to 5.3 plus 21.2 plus 2.6, and those numbers are pretty close as well. Yeah, they're actually exact. That's it. Okay, so that's our first simple series circuit using Kirchhoff's laws. Now you're like, well, why don't we just use simple series circuit math? Go right ahead, but I'm just kind of preparing you for more complex problems, which we're not there yet. We are still in a parallel circuit, which we can use just simple parallel math. But let's get some more practice, because especially this one, there's going to be 6 loops, and so we're going to want to draw 6 loops and get practice drawing those loops. Okay, step 1 is label all unique currents. We need to make sure we label them all. So I know in each branch, the current is split. I'll start off with the current passing through my battery, and then I know once I hit the first junction, I'm going to be going to the left, and this may be like I1. And then this is I2, and this is I3. I also like labeling my current 1, 2, and 3 to match the number that I'm calling my resistor, 1, 2, and 3. Second step is we are going to label all unique loops. So we're going to need to draw these loops. I always get in the habit of drawing from the positive terminal, and you'll see why. So there's positive, negative. So my first loop is going to look like this. My second loop is going to look and pass through R2. But because we want, a good question to ask is, well, are all loops meant to be drawn counterclockwise? No, they can also be drawn the opposite way. They can also be drawn clockwise. So I'm going to draw my third loop going around my outside, and we're going to see what that causes when we do our equations. Okay, that's only 3 loops, but I definitely see a few more. I see the loops inside of the branches themselves. So I see a loop right here, I'm drawing in green. I also see a loop right here, I'm drawing in green. And then I see one more loop that passes through 1 and 3. So maybe I'll draw like this, and I'm going to make it easier. I'm going to try to draw. Ooh, that's not that clean. Not like it's clean anyways, right? And then we want to label them. So I'm going to label this L1. I'm going to label this L2. I'm going to label this L3. And then you notice I got in the habit of just drawing them counterclockwise, but it won't matter. This is L4, this is L5, and then my blue is L6. Make them all smaller. So let's use our loop rules and our what happens when we're passing through and we get positive or negative voltages. Remembering that this direction of current that we drew is the direction of the electric field, and if our loop is passing in the same direction as the electric field, that means we are going from a high voltage to a low voltage. So like a 40 volts to a 0, 40 to a 0, or 40 to a 0. And we also need to be aware of which resistors are actually passing through. Like loop 3 is passing through the battery and resistor 3. It's not passing through R1 or R2. Okay, so let's do this practice. Loop 1 starts off at the positive terminal of our battery and then passes through R1 in the same direction of the current. So I see first we are passing through, right, in the same across the positive terminal of our battery. So we start off with this, and then we also see that we're passing in the same direction in our loop. So our voltage of our battery is added, and the IR, or the voltage dissipated by resistor 1, is subtracted. So I have 40 minus I1 R1 is equal to 0. Pretty much stating that the voltage dissipated in the first resistor is going to be 40. Back to like parallel laws. Loop 2, we again start off at our positive terminal. And I want you to be imagining, right? We're moving through here. And that's how our loop is being created. So that's going to be starting off with the positive 40 minus I2 R2 equals 0. Now this loop 3 comes in, and we recognize that it's done differently. We're doing it counterclockwise. Now that just means that instead of going across, leaving the positive terminal, we're going to the starting from the negative terminal, or like we're passing from high potential to low potential as we go left across the battery. So our loop is going against this battery. We're kind of taking off this way, and we are leaving the negative terminal. And that will mean I start off with negative 40 volts. As I pass through R3, I recognize that my loop direction is going in the opposite direction of I3. So I'm going against this electric field. I'm also going from a point of 0 voltage to 40 voltage. And so I'm gaining potential because I'm going against the field. So it's plus I3 R3. And you can see the difference between loop 1, loop 2, and loop 3 is just I've multiplied both sides by -1. That's the only thing. It's just the opposite equation. So it's still the same equation. So it doesn't matter if you do clockwise or counterclockwise. As long as you follow the rules, it'll still work. All right, let's knock out loop 4 and loop 5. Loop 4 is passing across. Let's make this a little nicer. Ooh. Like that's the way I like to see it, is I'm passing across R1. I'm going against I1's current, which means I'm going from a point of low potential to high potential. So I'm gaining I1 R1 voltage. So I1 R1 is a positive. And then as I'm passing across resistor 2, right, because my loop is this. That's my loop. As I'm passing across resistor 2, I'm going in the same direction as the current. Right, here's my loop. Here's my loop. Therefore, I'm going from high potential to low potential, so I'm losing I2 R2. That should be done in green. Let's do this in green. Minus I2 R2 is 0. And this is just stating that the voltage across each branch is constant, such as in parallel circuits. Loop 5 is the same, but with 2 and 3 instead of 1 and 2. So since I'm going against the field in R2, I'm gaining that voltage, or I'm adding it. And then since I'm going in the same direction as the electric field, I'm losing the voltage across resistor 3. And then loop 6 is really just loop 4, but R2 is now R3, meaning I'm passing across R1 first, right? So my first passing over is going against the current in I1. So this is going to be I1 R1. And then I am passing R3 in the same direction as the current. So this is I3 R3. Now, when you look at these, all this is pretty much saying is, hey, every single resistor has the same voltage, and it's 40. That's all this is happening. And so right now, it kind of seems unnecessary, and I agree. But let's start off with this before we get to more complex problems. The one thing that parallel does help us with is we have written the loop rules down. Now we need to label all the unique junctions. So it says use stars. I think I use J. I say J1 and J2. Unique junctions are any junction that exists in a unique way. So this one is J1 and this one is J2. And they are unique, but the same as the junctions on the other side because it's just kind of repeating it. So in J1, I see, actually, I is equal to, as the current is going in, is equal to I1 plus, and then there's this other current right here, which I guess we might be able to call I4. I did not label that. And so I is equal to I1 plus I4. Because I is going into the junction, I1 and I4 are leaving the junction. In J2, we have I4 coming into the junction, and then I2 and I3 leaving the junction. So I4 is equal to I2 plus I3. Now, you may see that, hey, I can just combine these, and I get I is equal to I1 plus I2 plus I3 if I substitute I4 in. And that's kind of what we've been saying before in class. All right, but before we move forward, we just need to use what we already know about circuits in this situation to solve for any unknown variables. So we do need to know that, hey, 1 over R tot is equal to 1 over R1 plus 1 over R2 plus 1 over R3. 1/10 plus 1/40th plus 1/5, and inverse that, and I get an R total, just so you can check with me, is equal to 3.08 ohms. So 3.1, so we can round 0.1 ohms. And again, remembering that R times I is equal to V, and that I times V is equal to P. Okay? So I'm going to pause this video. I want you to fill this out and verify that these, and then once you do that, we're going to verify if these values are correct using our junction equations. Okay, using what we know, we should have ended up with these values. Since we had a resistance of 3.1, 40 divided by 3.1 becomes 13. We also know that the voltage is constant across each branch, and so it's 40. And so if we do 40 divided by 10, we get 4 amps. 40 divided by 40, 1 amp. 40 divided by 5 is 8 amps, and we get this power. So we need to verify these values using your loop and junction equations. So I might say that, okay, let's do our junction equation, and that is 13 is equal to 4 plus 1 plus 8. Yep, that's good. And I think we can recognize that each of these is pretty much V1 is equal to V2 is equal to V3 is equal to 40. And so we just are recognizing that I1 R1 is equal to 40, I2 R2 is equal to 40, and I3 R3 is equal to 40. And then I think we can just recognize that as long as we've written these correctly as one minus the other equals 0, 40 minus 40 is equal to 0. Our power, we're just ensuring that 60 plus 40 plus 320 is equal to 520, and it does. That's good as well. All right, now we've gone through this. We're going to finally bring up a harder problem. I know this video is reaching 29 minutes, so bear with me. So we now have 2 batteries in this circuit, a 20 volt and a 40 volt. Let's first, we need to identify our currents. And I will start off with saying this current's going this way. I'm calling that I. This current's going this way. I'm calling it I1 to match R1. And there's a battery kind of pushing against us, right? This is like a positive terminal. But I might still think that I2 is going this way. It's not a powerful battery, right? It's only 20 volts, it's not 40 volts. So maybe it's not affecting the direction of the current. And we'll deal with issues with that when they come. Okay, let's draw our loops. I have my first loop. Let's draw that. It's my loop 1. I might draw a loop on the outside as my loop 2, recognizing that I'm crossing over this. I'm passing this resistor, and I'm also passing this battery in that loop. And my last loop, I'm going to start here, and I'm going to draw it counterclockwise because I want to start with my positive terminal of this battery. So I'm going to draw that loop counterclockwise. It didn't work. There we go. Starting with this terminal. So I have loop 1, I need to label loop 2, and then I have loop 3. Oh, I need to make that smaller, that's why. Okay, and I also want to identify that I have one junction, which I'll just call J1, even though it's only one of them. And let's try, I'm going to pause this video. I want you to try to draw or write down the loops for loop 1, loop 2, loop 3, and then I'm going to come in and show you what I've written down. Pause the video. Okay, so let's double check our loop equations. In loop 1, I'm exiting my positive terminal of my 40-volt battery, so I'm starting with 40 volts. I'm going in the same direction. Okay, I'm going in the same direction as my current in I1, so I subtract that, and I get 40 minus I1 R1 equals 0. Okay, my next loop, I have it going all the way around, so this one is passing through R2 in the same direction as the current, but then also passing the negative terminal of the battery and then resetting. So I have 40, starting with 40, minus I2 R2, minus 20, because I'm leaving the negative terminal. The battery is like taking away that 20 volts from this loop. And then loop 3, I'm starting at the positive terminal. I'm going against the current I2, or going against the electric field, so I'm gaining potential right there. And then I'm losing that potential in I1 because I'm going in the same direction as the current. So I have 20 plus I2 R2 minus I1 R1. Now, we can't use simple parallel math, simple circuit math. We can't because we have a battery in there. And once we have a battery in there, it kind of messes everything up. So we need to use our Kirchhoff's law equations to answer what voltages we have. We are given that the resistance of 1 is 10 and the resistance of 2 is 40. So I might write those equations down. Okay, I have 40 minus I1 R1, which is like 10 I1 equals 0. That's my loop 1 equation. I have loop 2 equation is 40 minus 40 R2, I2, I'm sorry, minus 20 equals 0. And then I have loop 3, which is 20 plus 40 I2 minus 10 I1 equals 0. I can also rearrange and set them like 40 is equal to 10 I1. I can do that, which that's our first step. So this could turn into a systems of equations, or we can just solve through this. Let's solve through this. I can start with my loop 1 equation. Let's do it. Loop 1 equation is 40 is equal to 10 I1 if I add 10 I1 over. And so I get I1 is equal to 4 amps. Okay. I can also do loop 2 equation kind of separately as well and see that this is 40 minus 20 is equal to 40 I2. So I get 20 is equal to 40 I2, and I get I2 is equal to 0.5 amps. And then I can use my junction equation, I is equal to I1 plus I2, and I end up with a total I of 4 plus 0.5, so I get 4.5 amps. And so I've got I1, let's plug these values into this table. I1 is equal to 4 amps, I2 is equal to 0.5 amps, and I have a total current, but that current I is passing through the 40 volt battery, so this is 4.5 amps. I also know that my current I2 is the same current that's passing through this battery because they are in line. They are technically in series with each other. So the current passing through my second resistor is equal to the current passing through this battery, just kind of going against the battery's push, but that's because the 40 volts is greater than the 20 volts. So I end up with an I2, just 0.5. This must be 0.5 amps, which makes sense that it's so much smaller because this battery is pushing against it. And then I can fill out the rest of this table. I see this as 40 volts. I see this as 20 volts. And then there's my 40 and my 20. And then I'm going to calculate my power as 160 watts, 10 watts, 80 watts, 180 watts, and 10 watts. And then it says to verify these results. I don't want to do any calculations. I just want you to make sense of how this 180 watts coming from this 40 volt battery is being conserved in this circuit, passing through resistor 1, resistor 2, and the 20 volt battery that's pushing against it. So you might want to think of like, is there a negative watch going on? So now, I'm sorry, this is a 36-minute video, so it's long. We just need to recognize that there are two Kirchhoff's laws problems, one that deals with junctions and one that deals with loops. Both of them are important when we get to complex circuits that involve multiple batteries. And we need to use these rules to decide on how the voltage is dissipated in the circuit, how thinking about potential going from high to low, thinking about the current as a direction of the electric field, so the direction of going high to low, and applying them in different scenarios, ones that we can't just use basic circuit math for, like such as series and parallel. All right, I will see you in class where we will get more practice in.